Hello everyone, this is the 7th lecture of vibrations and waves. Today we will carry on with coupled oscillators. We'll be solving a few problems, and we're going to start with double pendulum. So we have one object here with mass m, and this is length L, and another object also with mass m and length L. We call this object 1 and this is object 2. The displacement of object 1 is taken from the equilibrium point here, the line. So this would be x1 and this would be x2. We just give the system a kick and it starts oscillating, and we assume there is no damping. So there are no resistive forces, and we don't drive the system yet. This is theta 1 and this is theta 2. We make use of the notation omega 0 squared, that is L over G. How many forces do we have on each object? In the lower one we have mg, then we have a tension here, T. But you can already see that while this string is carrying only this object, the other one, the top one here, is carrying both objects. So we have different tension. So this we can denote as T2, and this one here as T1. Now this object has also feels also the tension from the other string, so it also has T2 and mg downwards. Alright, we make use of the small angle approximation. So T2 is about mg and T1 is about 2 mg, right? Because it carries both masses. The force that we are interested in is in the x direction, so that would be the sine theta times t. So sine theta 1 first, that would be x1 divided by L. And sine theta 2, that would be x2 minus x1 divided by L. Alright, the next step is to look at Newton's second law, write the differential equations for both objects. Let's start with the lower object here. So we have m x2 double dot. We have the minus sine theta 2 times t. So it's a minus mg t2, right? Minus mg times x2 minus x1 over n. That would be for the second object. Let's divide by m, make use of the notation above, so x2 double dot, we divide by m, we end up here with g over L, we bring everything to this side, so it's a plus omega 0 squared. I can already write times x2 here, and this would be minus minus plus. You take it to the other side, you will have a minus omega 0 squared x1. So this is equal 0. This is the first, or the second differential equation right? This is the differential equation for the second mass. We do the same thing with the upper object. So we have m. Now x1 double dot equals. Now what do we have here? First we have the minus t1 times sines theta 1, right? That wants to take us into the minus x direction. And we will have also a plus t2 times sine theta 2. And let's see what that would give us. So we have a minus t1 sine theta 1 and plus t2 sine theta 2. The t1 is 2 mg, so minus 2 mg, and the sine theta 1 is x1 over L. You see this? Okay. And the other part now is plus a T2, which is mg, and sine theta 2, which is x2 minus x1 over L. So x2 minus x1 over L. Right, we divide by m, we bring everything to the left side. So we have x1 double dot. Let's see what we have here. Let's look here. So we have 2 times, and that's going to be with a plus. So we're looking only at x1 components. So 2 times omega 0 squared, and there's another plus here when we bring it to the other side with omega 0 squared. So we have 3 omega 0 squared. So plus 3 omega 0 squared. Now we collect terms with x2. It's only this term, and that would be with a minus sign. So minus, this is x1, minus omega 0 squared times x2 equals 0. And this is the equation for the first object. So now we have 2 differential equations. Yeah, that should be right. Now we use the trial functions for the normal modes. So for x1, we plug c1 cosine omega t, and for x2, c2 cosine omega t. And this is the same omega, because if we're talking about normal modes, they would have to be oscillating at the same frequency. Alright, so now we substitute these back into the 2 equations. Now note that we have no damping, so things are either in phase or out of phase. So these trial functions should be fine. Alright, let's substitute things. And we start with the let's start with this equation. We have second derivative here. That would give us a minus omega squared times c1. And again, we don't need to carry on with this cosine omega t, because it will cancel out. Plus 3 omega 0 squared minus omega 0 squared equals 0. So this is the first equation, and then the second equation gives us minus omega 0 squared C2 plus omega 0 squared I'm missing a C1 here, right? And I'm missing another C. What is this? This is with x2, so this has to be C2. All right. Omega 0 squared times C2 minus omega 0 squared, that's x1, so times C1 equals 0. Now you could solve this equation as in the last time, or as you used to solve it at high school, but I'm going to teach you which works, right? It works completely fine as long as you don't have a problem which is complicated. So once you start having 3 objects and above, then it becomes a much harder way of solving it like this. So I'm gonna show you a different way of solving it, and we're gonna use this later on also for when we have 3 objects. Right, let's do it on this side. So in general, if you have instead of x1 and x2, I'm going to write x, y, and z, and we have the constants. So this would be your c1 and c2. So we have a1 x plus b1 y plus c1 z, and let's say that is equal to something here, d1, and we have a2 times x plus b2 times y plus c2 times z equals to d2, a3 times x plus b3 times y plus c3 times z equals to d3. And you can carry on with that if you had x, y, z, and so x1, x2, x3, and x4, and then you can have an n by n equations. So now what you do is you look at the determinant of these equations. So you can write here d that is the determinant. So that is simply a1, b1, c1, a2, b2, c2, a3, b3, and c3. And you take the determinant of these, and we call it d. I'm going to make use of it. So to find x now, what you need to do is the following. You take the determinant as before, but instead of having a1, a2, and a3 here, this is a3, you put d1, d2, and d3. So in our case, for example, we're going to put zeros because the right hand side is zeros. So here you would have d1, d2, and d3, and the rest is the same. b1, c1, b2, b3, c2, and c3. you take the determinant of this and you divide it by the determinant that we have there, and that should give you x. And for y, you take a1, b1, c1, and then you replace the second column with d1, d2, and d3. You take the determinant and you divide by the determinant we have here. And for z, the same thing. Okay, I'm not gonna write everything, so you have here with 1 and 2, and this would be the with d1, d2, and d3. All right, let's now solve the problem here, the two equations using this method. Maybe I'm gonna rewrite this now, so you're gonna have it also on this board here. So we're gonna put minus omega squared plus 3 omega 0 squared times c1 minus omega 0 squared times c2 equals 0. This is the first equation. We want to find c1 and c2. This would be my x and y in that method. And the second equation is minus omega 0 squared times c1, and then plus minus omega omega squared plus omega 0 squared times c2 equals 0. Yeah. So these are the two equations. Let's write the determinant d. That would be minus omega squared plus 3 omega 0 squared minus omega 0 squared. And here we have minus omega 0 squared and minus omega squared plus omega 0 squared. And this gives you minus omega squared plus 3 omega 0 squared times minus omega squared plus omega 0 squared. Right, this times this, minus this times this, and here minus omega 0 to the power 4. So this is the determinant. Now, what is C1? As we did on the other board, C1 now would be the determinant, which is similar to what we had here, but we need now to replace the first column with the right hand side of the equations. So 0 and 0 here. And the right side, the second column is the same. We have minus omega 0 squared, minus omega squared plus omega 0 squared. And this we divide by the determinant, which we found here. I'm just going to type D. This is C1 and C2 in a similar way. Now we take the determinant. Now the second column is 0. And the first one is the same as we have here in the determinant. So we have minus gamma squared plus 3 gamma 0 squared and minus omega. There is no gamma here, no damping. Minus omega squared plus 3 omega 0 squared and minus omega 0 squared. There is no damping in this lecture today. And we divide by the determinant t. And now you notice something. that where we say this is easy to do, it gives us just 0, right? The determinant here is 0 and the determinant here is 0, so C1 and C2 are 0, yes. This is one solution, but this is not the solution that we are looking after. What we want now is to find the C1 and the C2 that are anything but 0. And the only way that C1 and C2 can be something which is not 0 is that the determinant is 0. So if the determinant is 0, then C1 and C2 can be finite and not 0. So we put D equals 0, determinant equals 0, and from this, now, this is the determinant, so minus omega squared plus 3 omega 0 squared times minus omega squared plus omega 0 squared minus omega 0 to the power 4 equals 0. Now it's easy to solve this now, and the solution, as last time, don't forget you should get two solutions. We have two objects, and we should get two solutions for omega, omega minus and omega plus. So omega minus squared would be 2 minus square root of 2 omega 0 squared, and omega plus squared would be 2 plus square root of 2 omega 0 squared. Please verify this at home that you get this. So omega minus is about 0.76 omega 0. And if you substitute back now, we can't find C1 and C2, but we can find the ratio. So C2 over C1, in this case, would be 1 plus square root of 2. This is what I showed you last time. I didn't show you how we get there, but this is how you actually can get there. I hope you had some time to try it. So this is the plus 2.4. And omega plus is about 1.85 omega 0, and that gives C2 over C1, which is minus 1 over 1 plus square root of 2. Okay, so it's about minus 4.41. Now we can take any initial condition for the system to oscillate with, and using the linear superposition of its normal modes, you can describe that system. Now, a small note about the determinant here, the physical meaning of the determinant. This is enough space to show. If you have a determinant of for a matrix of size n, let's say, and let's take n equals 2. So if you have A11, A12, A21, and A22, and you're taking the determinant. Okay, so this is, let's say this is A, this is the determinant of this matrix, then you can think about it as follows. So you have one vector here, and this would be A11, and this is A12, A21, this is A12, and this is A22. Now it's easy to show that, this is a different color. If I'm building up this parallelogram here, then the determinant in this case would be the area of this parallelogram. Okay, so this is A. And in general, if n equals 1, that's simply the length. That would be the length of the vector. If n equals 2, then the determinant gives you area. If n equals 3, then the determinant gives you the volume. Alright, now let's go one step back here to this problem, and keeping everything the same here, what happens if I now instead start driving the system here? So if I use the red color now, so I'm driving the system here with some eta. What now happens if we do that? So eta is eta 0 cosine omega t. Let's see if we can make use of what we have here, and let's see if what is changing and what is not changing. If we look at the lower object here, the differential equation should be the same. So if we go to the Newton's second law, nothing is changing with respect to this second object. But for the first object now we have an addition, because there's no longer x1, right? There's also eta there. So sine theta 1 is no longer x1. We need now to take away eta here. So sine theta 1 is the following. And that changes the differential equation for this object. And it changes that here, because we will have another term that is with eta and L, so that is the driving term which is on the right side. So the equation here would have a non-zero on the right side. I'll write it here. When you look at, we have 2mg, right? We have 2mg, that's right here. We have 2mg, so I need to add now, I need to take away eta here, right? So there is an additional, on the right side, you're going to have plus mg eta over n. We divide by eta, so we have 2 omega 0 squared times eta 0 cosine omega t, but the cosine omega t is cancelled out. So on this side we should have now 2 omega 0 squared eta 0. Now make sure that you agree with this. This is x2 still, right? So I should write cosine omega t. This is cancelled out at this stage. I'm trying to make shortcuts, so not to type everything again. Normally it's not a good idea because you can introduce some mistakes that way. But now let's see here. What we'll have here now is simply 2 omega 0 squared times eta 0. on the right side. But now this is a big difference. You might think that, okay, so now we just do the same thing, and there is a big difference between the forced case that I'm driving and the initial case that we had. Now we know that the omega is my omega, right? And C1 and C2 will be determined now. They're no longer we're no longer looking only at the ratio of C2 over C1, but now we would be actually finding out what C1 and C2. There are no adjustable constants any longer in this case. So keep that in mind. So let's look what we will get in this case. Let's do it here. I can make use of this maybe. So the addition is this 2 omega 0 squared eta 0, and it should show up here. So we have the 2 omega 0 squared eta 0. The determinant is the same, but C1 is not the same now. C1 now has 2 omega 0 squared eta 0 here. C2 will also have 2 omega 0 squared eta 0. Because this is D1 and D2, right, for the determinant. So now we put it one time here and one time there. Yes, it should be like this. We're no longer looking at D equals 0. Now we can find C1 and C2. Okay? We can find C1 or we can find C2, not only the ratio. So this is C1. C1 would be the determinant here. Let's just write that. C1 equals 2 omega 0 squared eta 0 times minus omega squared plus omega 0 squared divided by the determinant, which I deleted, but I can just type. Let's type it here again. So minus omega squared plus 3 omega 0 squared minus omega squared plus omega 0 squared minus omega 0 to the power 4. This is C1 now. And this is my omega now. It's no longer the natural frequencies. And in the same way you can write C2. And now C2 is just this with the plus sign. So we have 2 omega 0 to the power 4 times eta 0 divided by, I will just type D here for the determinant. Okay, we have C1 and C2 now. So if I'm driving it with this omega, I can calculate exactly what would be the displacement of the upper object and what would be the displacement of the lower object. Now let's try and analyze what we have here, and let's see if it also satisfies some of our predictions. So basically we have this system of two objects, right? The pendulum. And the first question that we did last time also, qualitatively, was what happens if I just move this very, very, very slowly? What does that mean that I'm moving it very slowly? It means that omega is tending to be 0. Okay, so if I'm moving this very slowly, what you would expect that C1 and C2, or the first object and the second object, would have enough time to follow my eta 0. This is my eta 0, right? I'm moving from one side to another, but I'm doing it slow enough. So if I do it with omega, which is very close to 0, then this is my eta 0, and this is my C1 here, and C2, and they're both just following, in every moment in time, they're following eta 0. So C1 and C2, we would expect them to be equal to eta 0. Let's see if that is what we get here. When omega goes to 0, so if omega goes to 0, what we have up here is 2 omega 0 to the power 4. We have 3 omega 0 squared times omega squared, that is 3 omega 0 to the power 4 minus omega 0 to the power 4, that is 2 omega 0 to the power 2. So down here we'll have 2 omega 0 to the power 2, and up here we'll have 2 omega 0 to the power 2 times eta 0, so C1 equals eta 0 as we expected. And C2 is the same. C2 equals eta 0. Okay, because once this is 0, basically you get exactly what we have on top here, and at the bottom here is exactly what we had before. So C2 is also eta 0. Now, what happens as we start increasing the ratio increasing omega? So omega starts to go up, and we're looking at the ratio C2 over C1. C2 over C1. Well, first of all, C2, you notice that it's always, if it's not equal to C1, it's larger than C1. Right? Because there's a minus sign here, which makes this smaller, and it's the same determinant down there. So we know that C2 over C1 would start with the ratio 1. And then it starts increasing as we increase omega. So C2 over C1 becomes starts to become larger than 1, and it starts increasing until it reaches the value 2.4, which we had before. Now there is one frequency which is quite interesting. What happens when my omega, my driving frequency, is exactly equal to omega 0? Alright, let's look into this. If omega is exactly equal to omega 0, let's do C2 first. We'll have omega 0 here. So this whole thing is cancelled, and we have a minus omega 0 to the power 4. We'll have a minus 2 eta 0. So C2 will be minus 2 eta 0. What happens with C1? Well, if omega is equal to omega 0, then C1 is exactly 0. Now this is not so intuitive really, because what this physically means that there should be a frequency. If I drive this from side to side at that frequency omega 0, then what you would see is that this is going twice my eta 0, and this one would just stand still. This would be holding here, and this would be going happily from one side to another, and this is completely standing still. So this is not so intuitive. Let's make a figure. I can delete this. And then I will make a demonstration for this omega. I'll try. Okay, how would things look now? So instead of taking omega here, I'll take omega over omega 0. So I'm normalizing everything by omega 0. And the same thing here, instead of looking at C1 and C2, I look at C1 and C2 over divide by omega eta 0. And let's see what we know now. For C1, I'm gonna use red, and for C2, I will use blue. We know that both of them, C1 and C2, would start at point 1. That is the ratio. C1 over eta 0 is 1, and C2 over eta 0 is 1 when omega is 0. Right? When omega is 0, C1 and C2 are eta 0. So C over eta 0 is 1. So they start here. There are two natural frequencies for the system. This would be the lowest one. This would be the minus omega over omega 0. And this would be the omega plus over omega 0. Okay, what also we know is that the first object, the ratio between C2 and C1 is always larger than 1 until we hit that point. So I know that they both start from 1, but the red curve here should be lower. Okay, this is the first part. We also know that at point omega equals omega 0, so when this is equals 1 here, this point, the C1 is at 0. And at that exact point, C2 should be at minus 2. So now C1 would come from here, go up there, and C2, let's make this a bit, doesn't matter, and C2 would go something like that. C1, and this would be C2. All right, but to find out what happens here, all you need to do is to look at what is the sign of the C1 and C2 when you're after the omega plus over omega 0, and you would find out that this is a plus, so it has to come from there, and this would be a minus, so it has to go from there. And as omega goes to infinity, we know that the whole thing would go to 0. Of course, this doesn't cross here. We'll just go. Alright, let's try to make a demonstration now for this interesting point where this is standing still and this is moving from one side to another at a displacement which is twice the displacement of my hand. Let's try and see if I can find this frequency. I'm gonna try and find the frequency which has to be above the first natural mode frequency, right? And it has to be below the second one. And it's not easy to find. Here we go. Alright, you get the point.